Lecimy online od razu, czy nie?
Jeszcze chwilę.
Welcome. Welcome after the summer break, which was longer than we expected. Today we have the pleasure to have again a seminar from our photonics line seminaries. And welcome everybody on place, welcome everybody online. And today we have the pleasure of to listen to two talks. First talk will be given by Dr. Paweł Socha, who is a member of our photonic materials from the Institute of Microelectronics and Photonics. And Paweł will give a talk about his achievements in development new types of the fibers with the perovskite cores. And then we have the pleasure to have the second main lecture given by Professor Johan Trolles. And then I will introduce Johan a bit later. Now we start with Paweł. Paweł?
I have microphone, so. Okay. It's working. Yeah. So as you see or as you read, my topic is fabrication and properties of fibers with perovskite core. I have 15 minutes, so I try to talk just in general, what are we doing about the topic. So here is all outline of my presentation. So a few words about motivation, then why halides perovskite, then I will talk about the fabrication method, so about molten core method, and then we will move from theory to practice, and I will show and talk about the fiber preparation and characterization. Okay, so motivation. There is a class of optical fibers that it's very interesting because it joins properties of glass and crystals. There is a glass cladding and crystalline core inside. And we can use crystal properties in our fibers. As you can see on the presentation, mostly we use garnet crystals because we can have this laser action. But of course we can use this kind of fibers for sensing, as a light source. And we found that there is a gap and one material was not used before. It changed a bit later, but when we started, we noticed that halide perovskites were not used in these kinds of fiber. And of course, I guess most of you know about halide perovskites, but they have of course, many interesting properties like photoluminescence. They can be used as a sensor of X-rays or gamma rays. However, and of course, the production cost of this material is quite low, and they found a place to be used in many optoelectronic devices like LED, sensors, photodetectors, solar cells. However, they are hygroscopic, and because of LED presence, they are not environmental friendly. So it is a good idea to put some cladding just to omit these two problems. And when we started, there was no articles about this kind of fibers, but in last year we found that there is a group who crystallize perovskites directly inside the fiber. So this method is excellent. It grants the excellent quality of crystals. Crystals grow directly in the fiber, so we can prepare the fiber and then grow the crystal. And method can be used for both inorganic and hybrid perovskites. However, crystal growth is quite slow, and growth limitation due to ion diffusion makes some problem that we sometimes can obtain only very short fiber. But we were working on other methods, as I mentioned at the beginning. So we try to use molten core method, and with this method we can produce very long fiber in short time. We don't have this diffusion limitation, and we can make synthesis of perovskite during the drawing. However, we cannot obtain, at least at this moment, very good crystals, because crystallization is spontaneous and we cannot control it well. And of course, because we use the high temperature, this only inorganic perovskites can be obtained during the process. And how it works? We use the crystalline material. We put it into the glass cladding to prepare preform, and then we put our preform to the furnace, and we move our preform. Glass is soft enough to be drawn, and the crystalline material inside is completely melted. So when fiber leave the furnace, we obtain the fiber with the size that we want to have, and the crystalline core recrystallize again inside the fiber. We started, so we moved to the preparation of our experiments. So we started with the powders, lead bromide and cesium bromide. After mixing, we received the mixture of powders, and some of them were probably CPB. And then we put the powder inside the glass tube from Cymax glass, and this is our preform. And then, with help of Mr. Darek, who is sitting here, I was able to draw the fiber. So we put our preform, and we, let's say, feed the furnace with some speed. Of course, in this heating zone, crystalline material was completely melted, and then we draw the fiber. So the results. So we obtain the fibers. You can see the orange color, what is connected with perovskite. And we obtained fibers with those diameters. Like some parts are thinner or thick. And we move to we characterize all the fibers that we obtain with those methods. So starting with a single crystal X-ray diffraction, then we wanted to check photoluminescence properties of our fibers. We check, of course, transmission, and also we used scanning electron microscopy and energy dispersive X-ray spectroscopy because it's coupled with our SEM. So starting with single crystal X-ray diffraction, we can confirm that we received CPB and it's connected with literature. So yeah, we obtained the fiber with crystalline perovskite core. Then we check the photoluminescence properties. So we have like huge absorption band and emission band at 525 nanometers. And it's also, again, it's connected with literature. So yeah, definitely we have some photoluminescence, we have perovskite, but of course what's more important in fibers is transmission. So also we started with infrared and the supercontinuum to check how it works. And unfortunately, we have no transmission through the core. So yeah, probably crystalline core quality is not good as we expected. Even with long fibers, long fibers and short fibers. So we and of course we also check the UV light. Okay, too much. Whatever. We started with this setup without the filter, and we again have this transmission only with UV light going through the cladding. However, we put filter between our source fiber and detector and spectrometer, and we noticed that we have some green light. So yeah, we can excite the crystalline core and obtain the emission through, let's say, the core or next to cladding. And of course, we measure it with spectrometer, and these values are also similar. So it's interesting. And yeah, we also tried then to check when we will see the green light after excitation with UV light with different length of the fiber. So we started with like 40 centimeter fiber, and then we cut the same fiber just to have its shorter. Unfortunately, it's not visible here because of probably, I don't know, the computer, but you have to believe me that at the 10 centimeters we had green light going through the cladding. So probably we can use it as maybe as detector connected with some other light or components. But of course, for the shorter parts of fiber, like less than 1 centimeters, with several, let's say, parts, we could see that in one part we have even the green light going through the core. So it's like a small success, but of course we also tried to check what was the problem. So we again went back to single X-ray diffraction, and we see that there is several signal from the crystals. So we have evidence that it's not like real single crystal, but few crystals with similar orientation. And we went to SEM, and we noticed that in some part of fiber, we have some cracks and holes, what is probably the residuals after some air that was in the powder. And of course, as I mentioned, we made the EDS. So from this signal, we can notice also that we have some silicon and oxygen inside the core. So probably when the core is completely melted, we have some diffusion from the cladding. And just to sum up my presentation, so we designed and fabricated this fiber with perovskite core, with molten core method. We confirmed that there is perovskite in the core and exhibits the green light. And however, we still have to work with the crystal core quality. And some short acknowledgement, firstly for Łukasiewicz Research Network, for some funding that we obtained it, but also I would like to mention about the miniatura that I received, and we will continue our research. And thank you for your attention.
Thank you very much. We have time for one question, because Pavel was... Okay, go.
As I understand, the whole core of the fiber is made of perovskite. Of perovskite, yes? The whole core is perovskite. Let's say we want to have a monocrystal, but are there any attempts, or many there are articles about the nanoperovskite, nanocrystals?
Yes, there are some papers about that. Yeah, people just prepared some nanoparticles, and they put it inside the fiber. Yeah, definitely.
Okay, I think we have to stop. More questions will be later. Now we have to move to our main guest. And it's my pleasure to introduce you Professor Johan Flores. He is a professor at University of Rennes. And he's best specialist in the chalcogenide fibers. If you will ever have the possibility to visit his lab, it's really amazing to see what he can do and what quality of the fibers he can develop. I had the pleasure to work with Johan together. We had a joint Marie Curie training network project that we developed some interesting fibers. And also now we realized together the Polonium grant. That means there is still a possibility to bring new knowledge and collaboration, that if you have ideas, that's a unique opportunity, because Johan is very busy and he doesn't accept too many collaborations.
Okay, so thank you. So first of all, I would like to thank here Richard. I want to be here because it's a pleasure to be here. I remember that I was here 4 years ago for another project, but here we have a new exchange problem together. And today I will try to make an overview of our activity in our group. Glass and ceramic group at the University of Rennes. So first, we can just have a moment to see where is our city. So we are in France, okay? So this is the world. So France is here, okay? We are in Brittany, so not Great Brittany, but Brittany. In Rennes here, so you have a zoom here, so Rennes is just city. You have in downtown old city, in the center of Rennes, and this is our campus, which is not in the center of the city. Our campus, and this is our building. Our building is the main place for a big institute about chemistry, where you have organic chemistry and also inorganic chemistry. And our group, Glass and Ceramics group, is one of the inorganic chemistry research group. So this is how our group is working. We are different topics inside this group. First, we work on the synthesis, the structure of the glass, also sometimes on ceramics. We work sometimes we work on biomaterials, ceramics and glasses also. Since I would say 2010 now, we have new topics about energy conversion and storage. And one topics of this team is on infrared photonics and sensors. And Catherine Boussard is the leader of this group, and my colleague Bruno Bureau and Catherine are in this topic about infrared photonics. So my topic, we will focus mainly on this group, but sometimes I will speak about different research that has been done also in the other topics. Okay, so just for starting, why we are working on exotic glasses in Rennes? Because we have an history about that. Because 50 years ago, Michel Pouin, who is working on fluoride crystals, zirconium fluoride crystals, has made kind of, I would say, bad experiment with crystals because he has made the glass. And when he has made this glass, he was a little bit curious, and he has made the transmission of this glass, and he has observed that this glass can be transparent in the visible, like silica and silicate, and also in the infrared until 7 or 8 microns. So this is the first synthesis. It was the first synthesis of fluoride glass. So it has been done 50 years ago. In next March, we will make a kind of party about this, and with Marcel Poulain. Michel is died, I think, 2 or 3 years ago, and we will also have our Jacques Lucas, which is still emeritus in our lab. Okay, so now the outline of this presentation, we will discuss about exotic glasses and mainly chalcogenide glass. I will discuss about we will make a comparison between the oxide and the optical and the chalcogenide fibers, and we will discuss about optical properties, fabrication, and so on. Okay. So when we speak about chalcogenide glass, we have to define different range of electromagnetic wavelengths, electromagnetic range. Often we are speaking about short-wave infrared when the wavelength is close to 2 and 0.7. Mid-IR, it's depending on the community and depending on the publication. Mid-IR can be between 2, 5, sometimes 30. And you have also the long-wave infrared, the far infrared, which can be, I would say, after 10, after 20 microns. Okay. The interest of mid-IR is for infrared imaging. We have, I think, 20 or 30 years ago, a company has been created after the research about chalcogenide glass about infrared lenses. And this kind of lenses, for example, can be used for in car now. At the beginning it was for military applications, but now it's more and more civilian application. And this is an example of BMW car which has an infrared camera. You have here what the driver is can see in the visible, and this is the image of the infrared camera. Okay, so chalcogenide glass. What are chalcogenide glass? We call chalcogenide glass a glass which is based with at least one of these elements, elements, sulfur, selenide, or tellurium. And after fluoride, the first PhD student who has worked on this class of type of materials was Jean-Poisson, which is our head of groups now. It was a long time ago, so we have great experience about chalcogenide glass. So the team is, I think, probably the more important teams in, I would say, permanent position on chalcogenide glass. The best, I don't know, but very important team on chalcogenide glass since this first work. Made by Jean on chalcogenide glass. If we go back to the optical properties, and if we compare for the moment the transmission of bulk glasses, you have here the transmission of, for example, 1 millimeter thick samples. You have here the transmission of the classical silica glass, which is the most famous oxide glass. And you have the example of two chalcogenide glass. One is based with sulfur, and the second one is based with selenide. The first is slightly transparent in the visible. It has a red color, and they can transmit close to 13, 40 microns. And the second one is totally opaque in the visible, but can transmit light until 18 microns. For a bulk glass. Other interest, it will be interesting when we will we want to use a nonlinear effect inside the glass or inside the fibers. It's that the chalcogenide glass have a very high nonlinear effective index in comparison to fluoride glass or oxide glasses. Okay, how we make a glass, chalcogenide glass? The chalcogenide glass is made in a silica glass because it's totally different in temperature point of view. The TG of a silica is close to 1100 Celsius degree, and the TG of chalcogenide glass is between 100 and 300. So for making our glass, we are using silica crucibles. So in order to avoid the presence of oxygen and water, all the synthesis has been done under vacuum. So the raw elements are placed in a silica tube under vacuum. We seal the tube with a very high temperature torch in order to have a silica ampule where the chalcogenide raw elements are embedded inside. The ampule with the raw element is placed in a rocking furnace in order to have a good homogenization of the melt. And we quench the glass, has other glass materials. So chalcogenide glass has to be quenched in order to keep the glassy system, the vitreous state of the materials. And we have to anneal also the glass. This is a rocking furnace, and here you have an engineer from the lab which is quenching the glass, quenching sample in the big water container. Okay, so this is an example of a chalcogenide lens molded by the company Umicore, which is close to Rennes. Okay. In the topic of chalcogenide lenses, one part of the team is working to prepare graded index lenses in order to suppress the number of lenses in front of an infrared camera. And the first idea here is to use a partial crystallization of the glass in order to change locally the refractive index. And here you can see this is a rod of chalcogenide glass. A part of the chalcogenide glass is crystallized, and the crystals has a lower index than the glass. So by controlling the amount of crystals and the localization of the crystallization, they can make like this a kind of graded index lens. And this is the example of what has been obtained. This is a disc of chalcogenide glass which is partially crystallized. And you can see here, this is a refractive index measurements here. And this is the effect of the disc on a grid seen within an infrared camera. Okay. In the same topic, about the fabrication of chalcogenide lens, a lot of work has been done in our group in order to reduce the cost of the lenses, because you have seen that for making the chalcogenide glass we have to use a silica ampule under vacuum. For after each synthesis, the silica ampule is broken in order to get the chalcogenide glass. So silica is expensive. You have to use one crucible for each synthesis. So the idea here is there another method to obtain amorphous chalcogenide glass without using our synthesis under vacuum in silica? And here, starting elements has been placed in a ball milling, and just by in English, by milling the glass, by high rotation, and by I think it was close to few hours mechanical milling inside the systems, we have from the starting elements chemical reaction without the action of the temperature, just by the milling. And at the end, after we have at the beginning starting elements, and at the end we have amorphous powder. The amorphous powder has exactly the same TG than the glass, but of course it's amorphous powder. You don't have a lens, you don't have bulk glass. So after this, the amorphous powder is sintering by dark plasma sintering in order to obtain a bulk disk of glass. And this is an example that has been obtained here with glass. And sometimes treatment, heat treatment is also done in order to increase the mechanical property of the glass. And you have example here of 3 chalcogenide bulk glass made by these techniques. So there is no heat treatment at high temperature, and there is no need of silica crucible. The mechanical properties of chalcogenide glass are not the best in the material world, so a lot of work has been done in order to increase this kind of property by adding small particles, small crystals inside the glass. The idea here is to add numerous crystals, but very small crystals, in order to keep the transparency of the materials. And this work has been done in this kind of glass, which has a tendency to crystallize, and where it is not too difficult to control the crystallization by thermal treatment. Because if you have 2 large crystals in your glass, you can increase the mechanical property by the presence of the crystals, but you can also lose the transparency of your material. Okay. This is an example of what has been done in the topic of energy storage and energy, new energy. I'm looking to new energies. Generation, new energy. I don't know the word. It's the idea here is to use chalcogenide glass as a host for the rare earth, because chalcogenide glass has very low phonon energy, so it's a good host for rare earth. And the idea is to use wavelengths which is not absorbed by silicon in order to make some electricity. It's lost and it has been just absorbed by silicon. There is no transfer energy on electricity. And the idea is to use this kind of energy, which is not used by the silicon, in order to be absorbed by the rare earth in the chalcogenide glass, which can emit the light where the silicon can absorb the light and can transform all the energy of the spectrum into electricity. Okay. Another strong activity in our group is to use the chalcogenide glass not as bulk glass for lenses or for energy conversion, not as a fibers, but by using thin film. So here you have different example of what has been done with thin film. The first step is the same. We have to make the glass. We are chemists in the lab, so first we have to make the glass. We have all the equipment for making also thin film, and with collaboration with other lab, we can make some 2D patterning in order to have this kind of waveguides by using, it could be silicon at the beginning, but some layers of chalcogenide glass in order to make some sensors and waveguides in the mid-air. Okay. One activities also in the lab, which is not on thin film, because sometimes it's very important to prepare some waveguides, mainly for sensing application. And here the idea, it's a collaboration with a lab in Dunkerque. The idea is to photoride the waveguide inside the bulk glass. This is example which has been done in sulfur glass. The problem with sulfur glass is mainly when you want to photo inscribe the glass, you have a negative, you have formation of a negative variation of the refractive index. But if you want to make a waveguide inside your glass, inside your bulk glass, you need a positive variation of the refractive index. But they are using this in order to make a clad around the core, and they have made this kind of structure inside the bulk with this kind of helical form. But so by writing this form of a low index around the core, they succeed to make a waveguide. They succeed to use this. I think it was firstly demonstrated at 1.5. Or they say that it was not the best approach, and by changing the composition, they have found another glass which has a better behavior under laser inscription, where here you have a positive change of the refractive index. But when they have done that, they have observed that it was the size of the positive change of refractive index was too small in order to obtain waveguide. So they have chosen this kind of design. So in order to make a core, they have made a multi-core waveguide. So here there is not one, it's not several waveguides, it's multi-core. I would say here the different inclusion of high refractive index permit to have one waveguide. And they succeed also to split this waveguide in two components. And this has been done at 1.5 also. Okay. And by this method, they have also shown that it is possible to do that in the mid-infrared. This is a slide which is explaining the technique made, which is multi-core waveguide preparation by photo inscription. And this is what they have obtained at 1.5, and this is waveguide observed at 4.5. Okay, so now I will move to fibers, which is one of my main activity in the lab. Just to compare here, this is the different fibers that we can have in the literature, and in our case, our interest is to work on this kind of chalcogenide glass, sulfide or selenide, sometimes on telluride. And you can see here that depending on the composition, you can have different transmission range of the fibers. Okay. This is in order to be more accurate about the transmission, about the attenuation of the fibers. This is a comparison between different chalcogenide glass and classical oxide glass and heavy oxide glass. You can recognize here in yellow the attenuation curve of the famous silica, which is used for the telecom application. And you can see that after 2.4 microns, there is no transmission of the light in silica. By using heavy elements like tellurium oxide, for example, in this glass, TZN is a tellurium oxide base glass, you can move the infrared transmission to 3-4 microns. Of course, you can use Z-blanc glass. Z-blanc glass is a fluoride glass based with zirconium fluoride main component. And if you want to use longer wavelengths after 4, you have to change the matrix, you have to change the glass by using sulfur here in white, or by using selenide glass, or pure, not pure, but telluride glass here in red. So depending on the wavelengths that you want to use, you can choose the right glass. And for example, for your application, if you can use silica, use silica. But if you want to work close to 6 or 7, you have to change the materials. Okay. So I will try to start the video. I have a video of a drawing of a chalcogenide glass. Perhaps it's not a good idea to try to do that. I will try. Once again, where is the mouse? Ah, yeah, perfect. So perfect. You can be just on the second. on the second screen, and you can, and click on. But it doesn't work. It doesn't matter. Okay. Theoretically, I have a video of drawing of chalcogenic glass, but I don't need any video. The drawing of chalcogenic glass is exactly the same procedure than for drawing any other glass fibers. The idea here is to put a glass rod inside a furnace. For chalcogenic glass, the TG is low. The rod is very small. The preform is short. So our furnace is very small. The size here is few centimeters long, few centimeters large, and you have here the beginning of the drawing. Here, this is a drop of chalcogenic glass, which will fall down from the furnace. Here, this is the birth of the fiber. So the drop of the glass will fall down from the drawing tower. We break the drop here, and we fix the fibers on a drum. It's exactly the same procedure than with other glass. And the size of the fiber is controlled by controlling the speed of the preform motion here and the drum rotation speed. Okay. This is attenuation of a chalcogenic glass if you do any purification processes. In our raw materials, we can have a small amount of oxygen, we can have a small amount of water, and each time you have this kind of chemicals inside your glass, you will have the infrared signature of these chemical bonds. So if you have water, you will see the signature of water. This is one of the applications of the infrared, is to see chemical bonds. So when you have water in the fibers, you will see water. If you have hydrogen linked to the selenium, you will see the chemical bond between selenium and hydrogen. If you have oxide glass, you will see the signature. So the idea here is to remove mainly oxygen and water from our raw materials. So that's why in the lab we have developed high purity procedure, high purity synthesis. This is not the topic of today, but you can just observe here that we use some getters in order to trap the impurities. TeCl4 for trapping the hydrogen, aluminium, it could be also magnesium in order to trap the oxygen. And by several distillation of the glass and the different steps of distillation of the glass, we can have a better transmission of our glass. This is an example of an arsenic selenide glass. We still have a small amount of hydrogen linked to the selenium, so that's why we have here the absorption bond of the, which is a signature of the small pollution with a small amount of hydrogen. Here, when you have 2 dB per meters of ACH bond, it means that you have 2 ppm of hydrogen, because it's the absorption is 1:1 in this system. Okay. This is how we make the glass. This is how we make a single index fibers. Often, when you want to use your fibers in another lab with physicists, for example, they did, oh, but we need a single mode fibers. We need a step index fibers. Okay, so now we will see how we can prepare step index or, in any case, single mode fibers. The first method used with other glass, of course, but with chalcogenide is to use a classical rod-in-tube technique. Rod-in-tube techniques means that you have to make a tube with the clad glass. Sometimes, and you will place inside the cane of your core. So sometimes you have to draw a cane of the core before. Depending on the size that you want at the end, sometimes you have to stretch a first time a cane with this structure and put it again in another tube of the glass clad composition in order to have this kind of design. This is an example which has been done a long time ago with a sulfur system, and I think we have made also this kind of design with tellurium arsenic selenide, germanium selenide, because it's a very classical method for making step index fiber in chalcogenide glass. Okay, this is an example made with germanium selenide glass. So you can see here that there is a very small difference between the composition of the core of the clad, but it's just enough to have a beautiful difference between the two refractive index. And this is the near field image of this fiber at 1.5. This measurement has been done at 1.5. This is now a project we have with another colleague, David Lecoq. We know that we can photo write different refractive index in a chalcogenide glass. We know also that the chalcogenide glass is a good host for rare earths. Okay. Is it possible to combine this into fibers? So prepare core clad fibers with inside the core a small amount of rare earths. For making a fiber laser, it's a good start. But when you want to make a fiber laser, you need also to use Bragg grating in your fibers. If you want to make Bragg grating, one of the best ways is to photo-inscribe the Bragg grating in the fibers. That's why we are working on this kind of glass, because this kind of glass has been used, just before you have seen that, for making waveguides. So we know that this glass is a photo writable glass. So the idea is to use this photo writing glass, doping it with rare earths, and make single step index fibers, and perhaps in the future laser. Hard work, very hard work, but we have started to work on that. Okay. Main activities in the lab is to work on chalcogenide microstructure optical fiber. The method for making microstructure optical fiber in silica is to use the stack and draw. Stack and draw means that you have some rods, some rods of silica, capillaries of silica, you stack them together and you draw together the stack. We have tried that, I would say, 15 years ago with chalcogenide glass. So we have made fibers by stack and draw, but the loss obtained was too important. So that's why we have developed a method which is well adapted for chalcogenide glass, is the molding. The molding consists to use a silica mold, because silica is our crucible for making the glass. So here we will use silica mold. The silica mold which will be the negative shape of the structure that we want to do. So we need here capillaries of silica. We need guides, okay, into vacuum in a silica. This is a silica ampoule. By using the temperature, the glass, the chalcogenide glass, will flow down on the mold. So of course, at the end, we have to break the silica ampoule. And as you can see here, the silica mold is still embedded inside our preform. Okay, so you have the chalcogenide glass, but the mold is inside the preform. So we have to remove it. And here, chemistry is magic, because HF reacts only, at the beginning at least, react only with the silica. So we can remove all the silica mold from this, and you can obtain bulk preform, which has the geometry that we want to draw after. And depending on the mold, you can obtain different fibers. This is example of fibers obtained by this method. And by using this method, it's also possible to make this kind of fiber. This fiber has been done only 5 years ago by using 2 bigger holes in the first rings of holes of the fibers. That can permit to obtain a birefringence inside the fibers. And here you have the first chalcogenide glass, which is single mode, and you have polarization maintaining. 2 years ago, no, 3-4 years ago, we have already worked with this institute during an European project. It was through the PhD studies of Marcello Meneghetti and Xavier Forestier. The idea here is to use the procedure used in this institute with silica and silicate glaze, and perhaps with other glass, silicate, silica. That's it? No, that's it. The idea is to make green fibers with chalcogenide glass, and for that we have to use 2 glass which has 2 different refractive index. And you have here the 2 compositions we have chosen, G5 and G10. You have here the refractive index depending on the wavelength of the 2 compositions. And here, this is a structure which has been given by the lab here in Warsaw. And in red, you have the it's not the right side. I think it's the opposite. I think it's the opposite. I think it's the opposite. Because theoretically, the blue one here is the I index. So the I index is in the middle of the fiber. And after, we have more and more inclusion of the low index glass. And after, all of this stack will be put in a clad rod, which has exactly the composition of the blue. So I have to change the color of this curve here. It will be okay after. Of course, I make this mistake here. Okay, this is how we have done the fiber. So first, the stack. First, we have to make the glass, the 2 glass. I remember we have made 7 drawings in order to obtain enough rods for the preform. And this has been stacked here in Warsaw. And we have drawn it in our lab. First in a cane. This is the cane we have obtained. And the cane has been placed in a tube of the low index composition. And we have obtained these 2 examples of fibers. And we can recognize here the pattern of the core here. And this is the bigger one, and this is a small core we have obtained. Okay. How many time I still have? Yes, 5? Okay, 5. No problem. I can do it in 5. No, I think it's okay. I don't know. 40? Okay. This is a new method we are developing in the lab for making the microstructure optical fiber. The idea is to use our glass as a low TG. Our glass has a low TG, and if you compare the TG to classical polymer, you can see that it's the chalcogenide glass has a higher TG than the polymer that you can find, but it's not so far from polymer. So the idea is to use a classical filament 3D printer in order to produce preform with the chalcogenide glass. For this, we have chosen a very low TG glass, this tellurium 20, arsenic 30, and selenium 50. You have here the attenuation of the glass. And you can see here, sometimes I will not try to start the movie, but you have here the addition of line first, but line after lines, and layer after layers. You can construct like this a preform. And this has been done on this kind of design. For example, it was 3 years ago. Time is running fast now. This is our results. The height is very small, but we succeed to make fibers. We don't have enough preform to apply pressure inside the capillaries in order to well control the size of the capillaries, but we succeed to make the preform. We succeed to obtain fibers, and after we have seen light inside the core of the fiber, inside the hollow core of this fiber. Okay. Chalcogenide glass can be used also for supercontinuum generation. I have seen at the beginning that the nonlinear refractive index of the chalcogenide glass is very high. So by using this, by combining the high nonlinearity and the transmission in the mid-IR, perhaps it can be, perhaps it will be possible, and it is possible to generate new wavelengths in the mid-infrared. This is well known in silica. This is an example of silica where you are using a very high power at one wavelength inside the nonlinear optical fibers in order to obtain a supercontinuum generation. It has been done in chalcogenide glass in a microstructure. It has been done also in step index fibers by other groups, but here it's an example of our fibers. And here the pumping has been done by another supercontinuum. So we are using a supercontinuum generated in the fluoride fibers in order to generate another one for longer in another range for longer wavelengths until 9 and 10 microns. So I think I'm close to the end. Yes, I just have to speak about this important topic in the lab. After it's finished, I promise. Now go back to a single index fibers. So it's easier it's more simple to obtain. You have just a glass of rod, purified glass of rod. You make a single index fibers, and here the principle of this fiber evanescent wave spectroscopy is very simple. When you inject light in the fibers, so there is no clad. Okay, clad is the air. Okay, clad is the environment. If you apply a drop of chemicals, for example, on the surface of the fibers, part of the light is propagating at the skin of the fibers. When there is no absorbing environment, you have propagation of the light. But if you have absorbing chemicals at the surface of the fiber, you will have absorption. So if you have absorption, at the output of your fiber, you will see the signature, the chemical signature, the infrared signature of the absorbing environment. And this has been used for making medical diagnosis and other analysis. And I think close to 10 years ago, a company has been also founded by using this phenomena in a chalcogenide glass. Okay, so I will skip this. So it's possible to use also PCF for make sensing. The same idea using evanescent wave spectroscopy. And here it's a combination of supercontinuum generation and detection of infrared in organic compounds. I think I'm close to the end. This is also detection by using rare earths inside the chalcogenide fiber. Okay. I would like to thank all of my partners and the different institutes for their financial aids. And I would like to thank you for your attention. Perhaps here you have the dark side of the chalcogenide glass. Okay.
Thank you very much for the fantastic talk. Now there is a unique opportunity to ask some questions to our speaker.
If you have a question.
If you are not ready, I can start. I have plenty. My question is about graded index lenses based on the
crystallization.
crystallization.
Mhm.
How well you can control the profile and how fast lenses you can make?
I'm not strongly involved in this part, so how they can control that? I think they can control that by the duration of the heat treatment and the temperature of the heat treatment. And depending on this, you can, of course, if the temperature is too high, as an example, if the temperature is too high and if the duration is too high, you have a crystallization in all your glass. So by choosing the right temperature and right duration, you can obtain a profile. But after, I think you cannot obtain all the profile that you want. It's controlled by the refractive index of the crystals. So you have a kind of design that you can be obtained depending on the time and the temperature, but it's strongly linked to the crystals you have obtained. You cannot decide before a design, before the crystallization. You have to make different experiments and choose the temperature and stop your heat treatment when you have obtained the best profile.
This is more based on the experience than...
Yeah. Exactly.
Do we have other questions? Okay, then one more. You have shown the supercontinuum generation, this kind of the chalcogenide fibers.
Yeah.
Did you consider to use the chalcogenide fiber as a kind of the core of silica? Because this would give you some possibility to just to have the whole core, which is filled with the...
Yeah. We have, I would say, we have tried, we have not directly tried because it was a collaboration with the Max Planck Institute in Erlangen. So they have, because it's not possible to draw together the chalcogenide glass and the silica because the difference of the temperature is too high. When you draw the silica, I think the temperature is close to 180 Celsius degree, 100.
Silica is 1,000...
1,800. Yeah. So the chalcogenide glass disappear at its temperature. So you can feel after by a post-treatment. I think they have done that. They have tried that at the Max Planck Institute. It works if you are using very short piece of glass, short piece of fibers, sorry, but you still have strong absorption of the silica. So you generate supercontinuum, but the supercontinuum is also absorbed by the silica clad. So you have to find a compromise between the nonlinearity and the length of your fibers. So
this is not very practical approach.
I remember that they have done that on, I think the length was close to 1 or 2 centimeters. So 1 or 2 centimeters, it's waveguides, not really fibers. It works, but in a practical point of view, I think if you want to use and generate supercontinuum and you want to use it as a source for spectroscopy, for example, you need a longer fiber.
Okay. Can we ask people from online for the questions, or this is not possible with our current system? Pani Patrycjo, czy online może zadawać pytania w jakiś sposób?
There is a chat box, but I'm not sure if anybody has
Okay.
questions.
Do we have from the online questions? No. Okay, last chance for the questions for offline. Then last question.
Okay,
Really,
no.
I promise the last.
No, no worries.
If you have the anti-resonant fibers. We know that from the silica, although it is transferred up to 2.4 micrometers, you can obtain the transmission in the anti-resonant fibers up to 4.5.
Yeah. Yeah.
How is about the chalcogenide?
No. We have not clear calculation done of that, but just by comparison of what it has been done in silica, we expect that the transmission of the band gap fiber, the hollow core fiber, will be close to the end of a transmission of a bulk glass. So for example, silica, if you have a thin bulk glass of silica, you can reach transmission close to, you can transmit up to 3.5, 4 micron. The absorption is huge, but you still have a small transmission if you have a very thin layer of silica. For chalcogenide glass, this age of transmission is close to 18 or 20 microns. So we believe that in comparison of what has been obtained in silica, because now the silica can reach on the fibers the transmission of a thin bulk of silica, we believe that in an hollow core fibers, in chalcogenide hollow core fibers, you can reach 18 or 20 microns. Because after, for longer wavelengths, even if the light is propagating in the core of the fibers, the evanescence of the field will see the glass, the materials, and after 18 and 20, the absorption is very huge, as in silica.
Okay. I think we stop at this moment. Let's thank our both speakers again. And yeah, let's thank the speakers again. That's the first. Thank you, Johan, very much. Just small announcement that we are working to improve the technical quality of our online stream. And
It's mine.
Please attention for new announcement about our seminars. The next seminar will be already settled for the 13th of December, and we have the our guest will be who will be there? Karol Tarnowski from Wrocław. Thank you very much. Thank you online audience. Thank you offline audience. And now we start the networking. Thank you very much.